usual. Whenever I hand back a grade item like that, you should make sure I've actually graded it correctly. I have to do like the same bit of arithmetic to add things together that total up to like 65 or 75 points, and I have to do it like 60 times. So I'm bound to screw up at least once. And then I have to like enter those into Canvas correctly, and that's dicey too. So check that I haven't screwed up your grade. So I want to talk about trigonometric identities. And what is an identity? Well, let's start with this. We know one identity. I call it like the most important fact about trig functions. What does the Pythagorean identity say? Yeah, that's like one of the things that gets called the Pythagorean identity. I was wondering about trig functions. Yeah, absolutely. Whenever you have a right triangle, and those sides, a squared plus b squared equals c squared. If I'm going to think about trig functions, then this side length a I should think of as being like cosine of theta, b should be like sine of theta. So what does that fact say in terms of this triangle? This squared plus this squared equals that squared? The Pythagorean identity is the identity that says that no matter what angle you pick, cosine squared theta plus sine squared theta is always equal to 1. And when we say that a thing is an identity, we're saying that it's an equation, and that equation is always true no matter what angle you plug into it. So it's not an equation that you could like solve for theta, because this is an equation that's true no matter what theta is. And we know a bunch of others. For example, we know these identities that say that any of the trig functions can be expressed in terms of sines and cosines. What's tangent in terms of sine and cosine? Sine over cosine. There's a trig identity. Tangent theta is sine theta over cosine theta. No matter what angle you plug into that, there's a true fact. Cotangent is cosine theta over sine theta, the reciprocal of tangent. Secant theta is one over cosine theta. And cosecant. Nice. We have identities that tell us that some of these functions are even and other ones are odd. What's the cosine of negative theta the same as? Is cosine even or odd? Even. Right, cosine is the x-coordinate. The x-coordinate doesn't care if you rotate up or down. So what's cosine of negative theta the same as? Nice. There's an identity. That's a fact that's true no matter what angle you plug into it. Sine of negative theta. Negative sine theta. Sine is odd. Tangent of negative theta. Let's think in terms of slope. So I'll start at a slope at an angle of 0 and rotate up and rotate down. How do the slopes compare? Do they have the exact same slope? Ish, but like one of them is going down. So one of them is negative the other. So it's tangent negative theta. Negative tangent theta. Tangent is also odd. We have some identities that tell us what happens when you like add pi over 2. So tell me, what is the cosine of theta plus pi over 2? Well, let's make it easier. Let's make all of these minus, just to, maybe that'll help jog the memory a little bit. They're simpler looking identities. cosine of theta minus pi. Well, no, I want pi over 2 minus theta. Okay. Let's replace all of these with pi over 2 minus theta. Do you remember seeing some sort of symmetry identity that had something to do with cosine of pi over 2 minus theta? Maybe you remember like where in the notes that was? Yeah, that seemed right. What did you say? Negative cosine, not quite. If it were pi minus theta, absolutely. So here's an identity. Cosine of pi minus theta is negative cosine theta. Right, that's because if you go out to pi and rotate backwards, the x values are the negatives of each other. So let's think about pi over 2 instead. You rotate up by pi over 2 and start going back because of the minus sign. How do these two points where my fingertips are compare? They just have the x and y coordinates swapped. So sine of theta. Cosine of pi over 2 minus theta is sine theta. Sine of pi over 2 minus theta is cosine theta. Again, the xy coordinates swap. So what's the tangent of pi, same thing, pi over 2 minus theta? Yeah, let's think of it that way. So that'll be sine of pi over 2 minus theta divided by cosine of pi over 2 minus theta. Now, because tangent is sine over cosine, that's this identity. And what can I do with these two? Sine of pi over 2 minus theta is cosine theta. What's the denominator? So this is equal to cosine theta over sine theta, also known as cotangent theta. And this process, like that we did right there, where we like explored using other trig facts that in fact are just earlier on the page, is a lot of what I'm going to do today. What we're going to do today is think about if you have an identity that you think is true, one way that you can prove it's true is by doing some algebra, using facts that you know about trig functions already, and seeing if you can reduce it to like a truism. And that's what we'll do starting right now. So here's an equation which I claim is an identity. I claim that no matter what x value you plug into this equation, it is always true. And maybe before we go through the proof, like, if you just wanted to like check whether it seems true-ish, what's some stuff you could do to check this before we do anything else? So this is supposed to be like, both sides of that equal sign should be the same no matter what I plug into them. Cool, let's plug in an input. Using a calculator aid or not using a calculator aid? Let's use a calculator, sure. So, let's take this thing that I want to evaluate, and let's give me a number you would want to plug into it. Sure, 1. Especially since we're using a calculator, who cares if it's something that we can't compute by hand. 1 minus, parentheses now, 1 minus tangent squared of 1 divided by sine of 1 minus sine of 1 times tangent of 1. This will give us some output value, 3.03-ish, and now let's plug it into the other side too. Did I type everything incorrectly? Any silly typos? 1 minus tangent squared, and all of that's in parentheses, so it's all the numerator. sine minus sine times tangent, plug in 1. Okay. Let's also check tangent of 1 plus 1, parentheses matter. So I want all of that to be the numerator, divided by sine of 1. I guess those outer parentheses don't really matter. That's the same number? Awesome. So at least plugging in 1 says that these two things look equal. What's something else that one could do that would maybe be more convincing than plugging in one sample point? Yeah, you could look at a graph, right? Because that would be like if you're using a computer, just plugging in more sample points. Let's try that. So let's graph both sides of this and see if it looks true. 1 minus tangent squared of x divided by sine of x minus sine of x times tangent of x. All right. And the other side, tangent of x plus 1, close parentheses, divided by sine of x. Look pretty close. Nice. So I think these two things are the same. But there could be just some like really small error between them that the graph would never tell us. So if we want to really convince ourselves that these two things are exactly the same, let's do some algebra. So here's one strategy. When you want to prove that an equation is true, maybe you could just like take the more complicated side, do some stuff to it, simplify it, and get it down to the side that looks simpler. This equation have a side that looks obviously more complicated. Nice. So let's start with that more complicated side. Simplify it by doing whatever. Hopefully we can get it down to the simpler looking side. So you look at that more complicated looking side. What's some stuff that you could imagine wanting to do to that? Well, here's maybe a bit of motivation. There's like division. If I could see like a common factor between the numerator and denominator, I could cancel. If I want to find those common factors, I guess I better factor the numerator and the denominator. Do one of those two things factor in some obvious way? Does everything in the denominator have an obvious common factor? Yeah, what common factor do you see? Sine of x. Let's pull out that sine of x. All right, you pull a sine of x out of sine of x, you get 1. Pull a sine of x out of sine x tangent x, you get tangent x. Cool. All right. The top. So I give the extra comment in like my own handwriting, which is maybe hard to read. That like you can use the difference of squares formula to factor the numerator. How does the numerator factor? How many people remember the difference of squares? Let's write it down. In this context in particular. How's that factor? Well, let's just write it down and then we'll check it. In this way, does that look more familiar? And if you wanted to check it, you could totally just like FOIL, right? FOIL is set out, you get 1 plus t minus t squared. Middle terms cancel. And I chose t for a reason, because t is the first letter in tangent. So I see a difference of squares in the numerator. Let's use that. What does the numerator factor as using the difference of squares? 1 minus tangent, 1 plus tangent. Cool. So we've just factored the numerator and factored the denominator. The reason that was a sensible choice is in hopes of seeing something that cancels. Do you see something that cancels? Numerator and denominator have something in common? What do they have in common? The 1 minus tangents. Those cancel. By canceling them, we are left with 1 plus tangent of x divided by sine of x. Is that exactly what I wanted to get? Yeah. I wanted to show that this thing simplifies to that. What's one way to show that? Simplify it till you get there. Cool. So, that's what today's going to be all about. I'm going to mention some trigonometric identities. We'll try to prove it. And here's one strategy. One side looks obviously more complicated than the other. Simplify it. And notice, did we actually use any trigonometry facts in this process? No, we just did some algebra. Sometimes that's enough. Cool. Let's proceed. Here is another identity. So maybe I'll add this to America. So, on a lot of the, even the open-ended homeworks I've been, I think, reasonably lax with demanding that all the supporting details should be shown. On this particular homework, I'm not going to be. I want enough words written that I totally described every step. And on the previous page, all those words were factoring when you factored and canceling when you canceled. And that's enough detail to say what's happening. Sometimes you need more detail. Let's explore this particular example. So here's a thing that I claim is just true. Tangent of x times cosecant of x is just equal to secant of x. Let's try to prove that. Again, does this have a side that's obviously more complicated? Yeah. Let's take that more complicated side and try to simplify. A strategy I'm an advocate of, there's not an obvious simplification right off the bat. But maybe there will be if I just put everything in terms of sines and cosines. That seem like a sensible thing? Cool. So let us, as the suggested step says, express everything in terms of sine and cosine. What's tangent in terms of sine and cosine? Sine over cosine. And the of x is important in what's being written. What's cosecant? 1 over sine of x. All right. So, and that's the stuff that you can just make blindly, hoping that you see something after you do it. Do you see something now that that step's been made? What do you see? There's a thing in the numerator that's also in the denominator. It's all multiplied, so you can cancel. Giving you, I guess, just 1 over cosine of x. All right. That certainly looks simpler. Let's look at the goal. I want to get it to be secant. Is that secant? Yeah, 1 over cosine is secant, so let's just rewrite that in terms of secant. Cool. That feel pretty good? So here's one strategy if you want to prove a trig identity. If there are trig functions you don't want to walk in terms of, tangent, secant, cosecant, whatever, maybe if you've looked at the extra credit from a while ago that's here are a bunch of other trig functions. Maybe you want to walk in terms of x secant or x cosecant or varicine. Translate them into sine and cosine, walk with sine and cosine. Here's another one. Let us prove that tangent squared plus 1 is always equal to secant squared, and this comment applies to this particular identity. If you know a trig identity, you can use it to prove other trig identities. So that means that the even-odd identities you could use. We used in the previous one the rewrite in terms of sine and cosine identities. But let's try to prove this one. Let's try to prove tangent squared plus 1 is identically equal to secant squared. Is there one side that's obviously more complicated looking? tangent squared plus 1. I don't see anything obvious to do yet. There's not like any factoring I could do because it's a plus 1 instead of a minus 1. But I do see a tangent instead of a sine and cosine. So one idea you can always pursue is let's just rewrite that tangent in terms of sine and cosine. What do you get when you do that?
Sine squared theta over cosine squared theta.
Sine squared theta over cosine squared theta, because there's tangent of theta. And now we need a plus 1. And we just want to keep simplifying. And if you don't see any other ideas, just like do something that you see that looks useful. And regardless of whether or not like you want to follow, like, right, there's always something a little bit fake about pre-including the steps that I want to follow. And like saying, what do you think I should do next? There are a few things you could do next. One idea is whenever you see a fraction plus another fraction, get a common denominator and add those fractions. Let's get a common denominator and add those fractions. What's the common denominator you'd want to use in this case? Cosine squared theta. So let's do that. Sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. And you know what? Oh, and getting a common denominator is supposed to happen in the previous step, not this step. That's okay, I still have enough space. Now that we have a common denominator, in fact, the only step that should ever follow after you get a common denominator is probably add these fractions. I can't think of another reason you'd want to get a common denominator. Maybe if you want to like clear out the denominator, but then, yeah, well, whatever. You get a common denominator, you want to add fractions. Let's add these fractions together now that it's easy. I see sine squared theta plus cosine squared theta all over cosine squared theta. Ooh. Does an identity we already know look useful now? Yeah, what's the numerator of that thing equal to? 1. And that's by the Pythagorean identity. Does that suddenly look simpler than the thing we started with? All right, that's progress. Towards something anyway. Let's see if it's progress towards what we actually want. I want to get a secant squared on the other side. Do I have a secant squared on that side? Yeah, 1 over cosine is secant. So by re-expressing in terms of secant, we get exactly what we wanted. That proves the identity is true. Cool. So I think the next one, I just want to be quiet for a few minutes. Here is another identity that I claim is identically true. I claim that cotangent squared plus 1 is identically equal to cosecant squared. And I think I just want to be quiet. Come up with the proof. You know what? As you either get stuck or get down to what seems to be a resolution, go ahead and compare with those around you. and see if there are any foibles or differences you spot by just comparing what you've done with what someone else has done. All right, so let's see. People feel like they have just about a proof written down? So did anyone write down a string of equations, but didn't write down any wants explaining them? Cool. This is exactly what I don't want to happen on like the homework. Do that on the homework, especially on this one, I'll like say, well, that's like 50% credit at best. I want you to explain the steps, even if they seem like super obvious. If they seem super obvious, then it doesn't take much explanation, but include something. Even if the explanation is just like, I factored. Include that. Should we talk through the argument people used? Is there demand? It seemed pretty similar to the one you just did. Yeah. And in fact, similar enough that like, these two results are often also called the trigonometric identity, the Pythagorean identity, in that like they just follow because sine squared plus cosine squared equals 1 plus a little bit of algebra. So sometimes those are also called Pythagorean. Groovy. So let's start getting a little bit more involved. On this next page, we in fact see the exact same identity twice. And that's because I want to introduce the second time around a different approach on the same problem. So here's an identity that I claim is true. Cosine divided by 1 minus sine of some angle alpha is the same thing as 1 plus sine alpha all over cosine alpha. And I don't know, that looks complicated enough that maybe you don't even believe it. I mean, like, it's me, right? So you know that like I do things wrong all the damn time. Maybe I screwed up a sign or something. Let's see if this is actually correct before I try to prove it, because if it's just not correct, then it's going to be really hard to prove. In that, like, if you come up with a proof of an incorrect statement, that just means that you made an arithmetic error somewhere. So, let's try to convince ourselves that the thing is true. Let's graph it. Let's do it. Cosine of x divided by 1 minus sine of x. Looks like that. All over, well, the next one is 1 plus sine of x. All over cosine of x. Look pretty close to the same? Excellent. I think I believe it. Let's try to come up with a proof. So, taking a look at both sides, is there one side that's obviously more complicated than the other? Certainly not obviously. Is there one side that you would want to call more complicated than the other? Left side. I think I tend to agree. Why left side though? Yeah, the denominator looks more expensive to work with. So let's take that side, the more complicated side, and see what we can do with it. In truth, like, it didn't matter which side you pick on this one. Let's try to do that. So let's start with the allegedly more complicated side. Cosine alpha divided by 1 minus sine alpha. I don't see anything obvious to do. There's no factoring to do because the numerator and denominator are both like linear. I don't see any like cosine squared or sine squared to use the Pythagorean identity on. So there's no like obvious simplification. So instead what I'll do is I'll make it more complicated and hope to make it simpler in a different way than just undoing the complication. and maybe it'll work. And in order to motivate, let's just take a look at, here's what I'd like to wind up with. Tell me something different about that as opposed to the thing we started with.
One plus sign.
There's a 1 plus sign in the numerator. So I'd like to get like a 1 plus sign to show up in the numerator of this thing. Well, I can do that, right? I could just multiply the thing by 1 plus sign, as long as I also divide by 1 plus sign. So let's do that. Let's take this. This is exactly the same thing as cosine of alpha divided by 1 minus sine alpha multiplied by 1 plus sine alpha, 1 minus sine alpha, by multiplying and dividing by, plus 1 plus sine of alpha. That's the stuff that's always correct, right? You can always multiply and divide by the same thing, as long as you're not multiplying and dividing by 0. So this should be okay. And now let's mess around with that and just see what happens. So with the rule that you definitely don't just want to cancel these out, because you put them there in hopes that they would help you, what would you want to do with this next? Yeah, let's FOIL some things out. So I guess different ways of describing this stuff. You just said like multiplying. Maybe other ones you might use, or maybe you'd like to say you're FOILing things out. I guess the most technical one you could use is you're using the distributive law. So let's do that. And I wrote all of those because any one of those would have been a reasonable description of what's about to happen. Let's distribute this out. So when you distribute out the numerator, it looks like cosine of alpha plus cosine alpha sine alpha. What do you get when you distribute out the denominator? Let's see, FOIL is an acronym, right? First, outside, inside, last. First times the first is 1. Outside plus sine alpha. Inside minus sine alpha. Last minus sine squared alpha. How many people wrote down like exactly that without the 2 terms in the middle that are about to cancel anyway? Yeah, cool, great. I guess you also use like the difference of squares law or something. Cool. So, well, I guess I should like add a step to cancel these then. Which if you just did, that's great. Cosine alpha plus cosine alpha sine alpha all over 1 minus sine squared alpha by canceling sine alpha minus sine alpha. All right. What else do you see that looks useful? Cool. What do you notice what about that 1 minus sine squared is useful? So let's use that. Since that's equal to cosine squared alpha Gesundheit by Pythagorean identity, this is going to become cosine alpha plus cosine alpha sine alpha divided by cosine squared alpha. All right. That definitely seems like a sensible thing. What should we do next? Let's look at what we have and see how it differs from what we want. There's what we have so far. There's what we want. I only see one cosine in the denominator. So assuming I haven't made a mistake or something, maybe one of those cosines in the denominator will cancel with something in the numerator. Is everything in the numerator divisible by cosine? Yeah. So maybe here's an idea. We could factor a cosine back out of the numerator and then cancel some cosines. And maybe I'll do that, and then we'll notice a simplification we could make. I'm going to take advantage of the fact that I have erasable pens in a moment. So that is equal to cosine alpha, 1 plus sine alpha divided by cosine squared alpha by factoring. And the whole point of that factoring is now there's something that cancels. So what could you get out of canceling now? Well, I can cancel a cosine from the numerator and denominator. They're both divisible by cosine. That would leave me with 1 plus sine alpha divided by cosine alpha. I cancel. Is that exactly what I wanted? Cool. So, when you finish a proof, this I think is correct. You should look back at it and see if you could streamline it. So notice here we factored a cosine out of the numerator. In this step, we distributed a cosine through the numerator. So if you like, this step is just undoing half of what that step did. So we don't really need this step as long as we change what we did in that step. So here's where I'm going to take advantage of the fact that I have an erasable pen. It turns out I know what I want now that I'm at the end of the proof. Cosine alpha, 1 plus sine alpha. Let's just not distribute the numerator out. It didn't help me anyway. Next step still, cosine alpha, 1 plus sine alpha. Cosine alpha, 1 plus sine alpha. Oh, notice now I don't have to do this factoring anymore. So that step I didn't actually need now, and I can jump straight to the canceling. So at the end of a proof, you should look back through it and see if you can streamline it. When you're coming up with a proof, you're going to just make choices. You don't know if they'll be the right choice until you're at the end. Once you're at the end, you've made all the right choices. See if you could if there are any shortcuts you could take. Nice. All right, so there's one way to approach this problem. And you'll notice that step one was arbitrarily decide one of the sides was more complicated than the other and manipulate that side. Here's another approach to proving an identity. Let's just look at both sides of the equation at the same time. As long as you do the same thing to both sides of an equation, it's still the same equation. So let's do that. This time let's look at both sides of the equation. So let's prove that same identity. Cosine alpha divided by 1 minus sine alpha equals 1 plus sine alpha over cosine alpha. As long as we do something that's a valid manipulation of the whole equation, we still have an equation that's equivalent to the one we started with. So there's an equation we have. Well, here's the thing I see. It's annoying that there's like division in this equation, right? Can you get rid of that division? Yeah, you just like cross multiply by the relevant denominators. Let's cross multiply by all the denominators. So that means I can move this 1 minus sine alpha to the other side as multiplication. Cross multiplying transforms this equation to 1 plus sine alpha, 1 minus sine alpha, cosine alpha times cosine alpha. So this time we're working with the whole of both sides of the equal sign. We cross multiplied, and that's what it became. And our goal is just going to be to reduce this equation to an equation that's obviously true. So, you take a look at that, what do you see? Well, I guess it says to distribute, so let's distribute. Left-hand side is just cosine squared alpha. Right-hand side is 1 minus sine squared alpha. And ignore this if you would like. There's more than one way to come up with a proof. What looks useful to do next? 1 minus sine squared alpha is cosine squared alpha, so let's do that by the Pythagorean identity. 1 minus sine squared alpha equals cosine squared alpha. So this whole thing becomes cosine squared alpha equals cosine squared alpha. Is that an equation that we know is true? We have now reduced the identity we wanted down to cosine squared alpha equals cosine squared alpha, which we already know is true. That means that the identity we started with must in fact be a true identity. Cool. So, all that this pack contains, I'm running low on time, low enough that I don't think we have enough time to do another one, is more examples of the same thing. You can build new identities from old. We will start by proving that 1 plus tangent psi over cotangent psi is equal to tangent psi. We will prove this identity. Those two last ones, that'll be our goal for next time. Maybe we'll get to that last one, maybe not. There's an extra credit advertised. There's nothing special about this, but just grid functions. You can prove identities involving anything. Extra credit, here are some identities to prove. Prove those identities by doing stuff to both sides. And then on Thursday, I'm going to have like a group activity day in which you'll walk with some other people and prove some identities and find something in. All right. Cool. So, between now and, this class doesn't meet Tuesday, right? Okay, between now and Wednesday, I'd appreciate if people would take a look at the homework in Canvas for today. It'll be some more identities like this. Maybe go through and come up with a draft of ideas for how to approach these remaining identities. That'll make our walk on Wednesday much lighter feeling. Otherwise, anyone planning on dropping by my office now, maybe to present some extra credit because they did a bunch of extra credit? Anyone planning on doing that at some point during the semester? Oh, okay, then I guess there's no rush. I just know that I tend to get really busy at the end of the semester because of it. Nice. Okay. I'm absolutely done. I'm terrible at saying goodbye.